because math is a language, right? So some of these are easy to come up with, and some of them are a little more challenging. Now, when it comes to the x-intercepts, all right, this has already been factored for us, which is a big win, right? So you look at each, you set each of these is equal to 0, and that gives you your x-intercepts, okay? But equal to 0 just basically means it's the opposite sign, the inverse sign of whatever you see, right? Because I'll just do 1. If x plus 2 equals 0, right? Then we subtract 2 from both sides, we get x equals -2, right? This happens for all of them. So the x-intercepts are when y is always going to be 0. So -2, 0, +4, 0, and +6, 0. Okay, those are pretty easy. The y-intercept is going to be when x equals 0. Okay, so we're going to get rid of these in a second. But what you're saying is this is 0, this is 0, this is 0 for the y-intercept. So I am going to graph this, but when you have the x-intercept, it means y is 0. The y-intercept is when x is 0. Now, when x is 0, we already have this. That equals, it's all multiplication. -1/2 times 2 times -4 times -6. You see this? That's what's left. Well, when we multiply this out, -1/2 times 2 is -1. -1 times -4 is +4. +4 times -6 is -24. Now, it's not just -24. Remember, the x is 0, so the coordinate pair is 0, -24. Okay? Now, the degree. Okay, I've got to get rid of, shoot. I got to get rid of this. Okay? Now, the degree is the highest order of x. But right now it's not multiplied out, right? It's factored. So this is factored. Do you remember polynomials? The general expression is like ax, it could be anything, but to the 4th plus b x to the 3rd plus c x squared plus d x plus e. This would be a 4th degree polynomial, and P.S. A would be called the lead coefficient. So this is actually, we answered 2 and 1. So we don't actually have to multiply this out, but if you can comprehend that when you multiply this out, you have 3 different x's, so the degree is going to be 3. The lead coefficient, when you multiply everything, these are all 1s. This is a 1, 1, 1. So the lead coefficient is just what's up here. Okay? Now, end behavior has to do with degree, okay? And whether or not this is positive or negative. The easiest way to talk about this is to do a basic graph of a line and a basic graph of a parabola. So a basic line, okay, something like this is positive, something like this is negative, right? And this is y equals x. So that's a odd degree, okay? Odd, right? Remember our evens and odds? So for this, for just a line, when the lead coefficient is negative, you're going to have, when you go infinite negative, you have a positive function. Remember, because this is the x, this is x, and this is function of x. So when you go infinitely negative, you end up infinitely positive for an odd degree. When you are infinitely positive, you end up with an infinitely negative for an odd degree that has a negative. So odd degree, negative lead coefficient. Odd degree, positive lead coefficient is the opposite. Okay? Now, let's look at a y equals x squared, see, I'm having all my technical difficulties, which is an even degree, basic parabola, right? This is positive, this is negative, right, on a basic parabola. So in an even lead coefficient, or an even degree, when the lead coefficient is positive, when you go infinitely negative, you have infinitely positive, infinitely negative, and the other way is the other way. Both, if you go infinitely negative, you have negative, infinitely positive, you still have negative, okay? And this is the lead coefficient is negative, the lead coefficient is positive for an even degree, okay? Well, we're going to go back up here. So we have an odd degree, and I erased that, but what was odd degree? Odd degree was like a line. And lead coefficient negative was like this kind of a line. So as x gets infinitely positive, infinite positive, this is going to get, infinitely positive actually is going to become negative. Infinite negative, that means, remember, we're diagonally like this, so our function is actually going to end up going positive. Okay? Now, let's get to our graph, our actual graph of this line. I shouldn't write why it's function of x, but okay. So remember our intercepts, -2, 4, 6. So -2, 4, 4, 6, right? Sorry, I should get rid of that other little accidental dot. These are our, so, and we know it's coming down from here to cross there, okay? Because it's going to have this kind of orientation, but it's going to squiggle because it's degree 3. Now, our y-intercept, remember, was -24. Now, we don't have room for -24. It'd be way down here. But let's do some, this is what I do as a teacher, is I do that to show that it's like it's not to scale anymore. And I just declare that this is -24. Okay, so this is 0, -2. And now what's happening, now we don't know if it actually loops before, technically we don't, but it loops afterwards. Right close, it comes down here and then it turns, okay? We use the integral, which is calculus, to find out exactly where it turns and why, and we'll figure that out a different day, right? But it's gonna come up and cross through here, and then it's gonna curve again and come down. Because degree 3 means you have 2 turns. So whatever degree you have one less turn. So a line has 0 turns, right? A parabola has 1 turn because it's degree 2 with 1 turn, right? Degree 3 has 2 turns. This is the essence of the sketch, okay? It looks like this. And here's 4, 0, and 6, 0, okay? Now, did I do this opposite backwards? I don't think so. As x goes to -infinity. Oh, sorry. When x, it's the opposite. I did. When this is x goes to positive infinity. No, I did that right. Sorry. I wrote it down incorrectly. When x goes to positive. Oh, it is opposite. I'm wrong. As x goes to positive infinity, this goes to -infinity. Yes, as x goes to negative, I don't know, I'm losing my mind. Okay, now, yes, it's baby driver. Let's look at Desmos for a second, and let's put our actual equation in, okay? Y equals -1/2. We're going to do exactly what we see. X plus 2, hopefully you had it written down, x minus 4, x minus 6, okay? And here is the graph. So we see that this is correct. And here's the graph, okay? So there's the spot 2, 0, 4, 0, 6, 0. This down here, you'll see it, negative 24, okay? And this is what it looks like. But the behavior is all happening in the middle, right? And there you go. Now let me just show you. I took the integral just for myself. I'll show you that another time. And it becomes this equation. -1/2. Oops, shoot. 1/2 x cubed. Oh, excuse me. No, I'm writing back. I'm writing in the same thing again. This is 3/2 x squared. This is what's called the derivative of our. So this is calculus. This is our original equation. This is a little bonus for those of you playing at home. This is the derivative, and you're going to see how these equations interact. Okay, 8x minus 2. Okay, now, I know this might be weird to see, but look at this. Where the blue one, so the blue one's the derivative of the red one. Where the blue one crosses 0.2, can you see that? 0.26297. That is exactly the x-coordinate of this vertex, 0.26297, okay? Oy. And again, where the blue one crosses 5.07037 is exactly the coordinate of the x for this vertex, 5.07037. That's why we take the derivative, because it helps us see a little bit also what is going on in like a double, in a different way. And in fact, that it should line up that this apex crosses down with other points along here, okay? This is why calculus is useful, because it helps you understand the curves. Well, obviously it has other uses too. Okay, back to our problem, notability. Hopefully we answered it. Let's oh boy, we're going back to the frozen. So maybe we've got to deal with frozen. Hey, thanks for tuning in. I really hope this was useful to you. Also, please like, subscribe, share the whole shebang, because it just helps the algorithm and I really appreciate it. And it's good to see you. See you next time.